Hello, this is section 2.5 for Calc AB part 2. With this textbook, they added logarithmic differentiation to this section. So I wanted to make sure we went back and covered this concept because it's a really important, very useful concept. So, and sometimes necessary. So logarithmic differentiation is a convenient method to use logarithms as an aid in differentiating non-logarithmic functions. Okay, so what this is referring to is you'll notice that y equals, you have 1 plus x as your base raised to 1 over x. And the problem is you've learned how to do something similar to this. So that's what I have here. You've learned how to do y equals 3 to the 2x. And in order to do that derivative, you know it's natural log of the base times the original exponential, and then you have to use the chain rule, times the derivative of the exponent. So watch how we can demonstrate using logarithmic differentiation to solve. And this will show you what we mean by logarithmic differentiation. So in order to do this, you're going to take the function and you're going to do the natural log to both sides. So natural log of y equals, and when you natural log this side, you can then pull the 2x down in front. So 2x times natural log of 3. All I did was natural log both sides. Now, we just learned a concept called implicit differentiation, when you cannot get y by itself. Now, you can in this case, but let's go ahead and use it and see if we get the same answer. So we're going to start from the left and do the derivative. So this becomes 1 over y, but then we have to multiply by the derivative of the inside. So we'll have to put a dy dx here. Equals, now be careful, 2 and natural log of 3. Those are just scalars technically. So x is your only variable. That's a linear. So the derivative is just going to be 2 times natural log of 3. So now you have to get that dy dx by itself. So multiply the y over to the other side. So we're going to have dy dx equals 2 times natural log of 3. Now when I multiply y over, isn't y equal to 3 to the 2x? So let's write that. Instead of y, I'm going to write 3 to the 2x. And isn't that what we just had up here? Natural log of 3, 3 to the 2x, and there's my 2. Oh, you get the same answer. So if you happen to forget that nice little rule, then you could use logarithmic differentiation to figure it out. But this hopefully proves to you that it works. Okay. Now, coming back to the notes, you don't have a choice. You have to use logarithmic differentiation to solve this derivative. All right. Because this is not a number here. You can't do natural log of the base. That only works when it's a number that's your base. So in order to solve this, you've got to get this 1 over x out of the exponent world. So by natural logging both sides, I don't know if that's a true term, natural logging. Anyways, natural log both sides, and that will allow us to pull that 1 over x down in front. And that's what we need to be able to do, because now we have derivative rules that we can now do this derivative. So here's that 1 over y times dy dx. That's the chain rule. Now here I decided to do, it looks like I did product rule. You could easily do quotient rule, low d high minus high d low over low low. I'm actually a little surprised I did product because I don't typically like to work with negative exponents if I can avoid it, but it works either way. Remember, we've talked about different paths you can go down. Okay, so I got this first times derivative of the second plus second times derivative of the first. Then it looks like I cleaned up the negative exponents. And then you could get a common denominator and combine those if you want. But the main thing is you've got to get this dy dx by itself. So I had to multiply over the y, which is what I'm doing here. And then if you left this answer, that is perfectly fine. But we know what y equals, so we replace that y with the 1 plus x to the 1 over x, and this is an answer. Now, your multiple choice answer would probably get a common denominator and clean it up a little bit more, but if this was on a free response, you could stop right there. You could even stop at this step as well. Okay. All right, so here's another one where you have to use logarithmic differentiation because you don't have a number as your base. So natural log both sides, which is what we did. Pull the x over 4 down in front. And that's perfectly legal. That's just a log property. And then from there, you're ready to do the derivative. So I did this derivative. Remember, natural log sends the argument to the denominator times the derivative of the inside. And then over here, I did the product rule again. And then just solve for your dy dx. Move it to multiply over the y. Okay. All right. And then this last example is just another demonstration. And this one, actually, you don't need logarithmic differentiation, but it's just another one. What I like about this one is when you do your derivative, you cannot get y by itself easily. So we use implicit differentiation. And when you go to do this, tangent turns into secant squared times x, and then you have, not times, secant squared of xy. But then you have to multiply by the derivative of the inside, and that creates a binomial because you have to use the product rule. So first times derivative of the second plus second times derivative of the first equals, and then over here that just turns into 2 sine of x. Now, what I like about this is you have a dy dx stuck within a binomial. So it's another one of those examples where you have to distribute to break it free. Then you can solve for dy dx. Move everything over that doesn't have a dy dx, then divide. So that's a good algebra problem to practice. Okay, but this logarithmic differentiation concept is really nice, and just there's some times where it's convenient to use, but then there's times where you have to use it. So you need to be very comfortable. Okay. All right. Let me know if you have any questions. Thanks.